Hello everyone. So let's start today's class. So as I mentioned in the previous class, we missed one class in October because of my because I attended a conference. So I'm recording this video. So and then in this class, so I will explain about the basic concept of pipelining. So as I mentioned in the previous class, the pipelining is the very important concept you need to learn in this course, okay? But so I believe the basic idea of pipelining is very simple. So I believe everyone can understand the basic idea of the pipelining easily. So actually the idea is very easy to understand, but actually detailed implementation is a little bit tricky. Okay, so okay, let's start the class. So in the previous class, so we learned about the hardware architecture of a single cycle processor, right? So we define how an instruction is executed in a processor, in a RISC-V processor. And then I explained about the required steps for executing an instruction, right? So like the instruction fetch, instruction decoding, and then register read. So, and then execution by ALU, and then memory access, and then write the data to the register file. Okay, so these are required steps for executing an instruction. Okay, and then based on these required steps, we define the function of a data path element, and we just connect the data input and output ports of the data path element. So it is because the data is given to a data path element, and then this data path element generate result, and then result is also transferred to the next data path element. Okay, so and then so the data is also processed, and data path elements also have control port, right? So and then I mentioned that the control signal determines the operation mode of a data path element, right? So in the previous class, we defined the control unit in a single cycle processor, right? Like this, okay? And then control unit generate control signals based on the input instruction, okay? So we define the two steps, okay? Two steps of the control unit, like a main control unit and then ALU control unit. So it is because the most control signals can be determined by OP code. So the pin number 6 down to 0. So that is those are the OP code of an instruction. And then actually the main control unit can generate the most control signals using OP code, okay? And then in order to generate the ALU control signal, then we also need to check the function 7 or function 3 fields of an instruction, right? And then one student asked about the control signals of store instruction, and then the students asked about the mem read control signal for the store word instruction. So and then obviously the mem read signal should be 0, right? 0 for the store instruction, because the store instruction does not read data from the data memory, right? And then mem write obviously should be 1, because the data is updated. It's written to the data memory, right? So I want to clarify these control signals for store word instruction. Okay, so and then I mentioned the performance issue of a single cycle processor, right? So actually the architecture of a single cycle processor is rather simple, okay? But the problem is that the latency, the sum of delays of this data path it will be very long, okay, for the single cycle processor, because when we calculate the critical path, that is the longest delay of this single cycle processor, and then that is the delay of the single cycle, the critical delay of the single cycle processor is the sum of the delay of instruction memory, register file, ALU, and then data memory, and also register file write. Okay, so actually this is very long. Then I mentioned that the execution time of a computer system is proportional to clock period. So if the delay of this combination logic is long, then we need to set the long clock signal. So we need to set the long clock period for the clock signal, right? So which means that clock frequency becomes low. It decreases. The clock frequency is decreased, right? So actually the frequency is the inverse of the clock period, so which means that the frequency is decreased than the performance, because the performance is also the inverse of execution time. So if the clock frequency is decreased, then the performance will be also decreased. And then I mentioned that this is the critical issues in a single cycle processor. Okay, so then how can we improve the performance of RISC-V processor? So in this time, so we will learn about the concept of pipelining. Okay, so let's see the analogy of pipelining. So actually, as I mentioned, actually the basic idea of pipelining is a simple, right? And then I believe everyone can easily understand the basic idea of pipelining. But so I will explain with an analogy. So let's think about, so let's assume that we are laundering our clothes. Okay, so and then actually we need to perform 4 different steps for laundering clothes. Okay, so for example, we need to use the washing machine. Okay, it's a washing machine, and then this is the dryer, and then we need to fold the dried clothes, and then we need to store the dried clothes in the closet. Okay, so let us assume that for the one clothing, we need to perform these 4 different steps. Okay, the washing machine and dryer, then folding clothes, and then we need to store the folded clothes to the closet. Okay, so and then let us assume that so each step takes 30 minutes. Okay, half an hour. So for the clothes A, the one clothes is so actually in order to store, so in order to complete these whole tasks, then we need to use the washing machine first, and then we need to use the dryer, washing machine dryer, and then folding, and then close it. Okay, so for the one clothing, so we need to consume 2 hours. Okay, because so as I mentioned, each step takes 30 minutes. And then for the next clothing, sorry about that. For the next clothing, we need to also use the washing machine, dryer, and then folding, and then closet. So we require another 2 hours. Okay, and then for the third clothing, so we also need to take the another 2 hours, and then another 2 hours. So in this analogy, in order to complete the full clothing, so in order to complete laundering for clothing, then we need to take 8 hours, okay? Because there are, so for each clothing, we need to take 2 hours, and then there are 4 clothings. So we need to consume 8 hours. Okay, but what's the problem? So it takes long, right? So that obviously it takes long, but we can observe that. So actually, let's focus on the, okay, let's focus on the, this timeline, okay, this timeline. So actually for this clothing A, so actually for this timeline is the first 30 minutes, then we need to use washing machine, right? Washing machine. But how about these 3 steps? So actually we do not use dryer, and we do not fold clothing, and then we do not use closet, right? Closet. So these resources, so we can say that this is a kind of hardware resources. It's a resources. So these resources are wasted because only for this time slot, is the first 30 minutes, we only use the washing machine only. So we are wasting these resources. And then for the next 30 minutes, we use the dryer, but we do not use the washing machine, and then we do not fold we do not fold clothing, and the clothes, and then we do not store clothes on the closet. So these resources are wasted. Okay, so we can observe, so this is the serialized task. Okay, so actually for one task, for the task A, and then this task A occupies all resources like washing machine, dryer, and then folding, and then closet. But if we just divide the time slots for each resources, then we can observe that for each time slot, for each step, some hardware resources are wasted because they are not used. They are in idle state. They are not utilized. The waste of resources. Okay, so if resources are wasted, you want to avoid this situation, right? So we have 4 resources like here. So we have 4 resources, but for each time slot, so we actually 3 resources are wasted, so are not used. Okay, so that's the problem. So actually the hardware engineers cannot see this situation. Okay, so actually if certain hardware resources are wasted, so it's not a good situation, right? So we can pipelining. It's a pipelining. We can pipeline the steps for laundering, like this one. Okay. So what is this pipelining idea? This is called the pipelining, right? So pipeline. So it's just it's a kind of it's a pipeline. The pipeline is just connected, but you can understand the basic idea of pipelining like this. So for this task A, so cloth A, so for the first 30 minutes, and then this task just occupies washing machine, right? And then for the next 30 minutes, then this task A occupies dryer. And then, so for this timeline, though, this washing machine is not occupied by task A, right? So, which means we can just assign new task to washing machine because the washing machine is not used now for this time slot. For this time slot, this washing machine is not utilized by task A. So because the task A is using a dryer. So in this time slot, then we can assign task B to the washing machine, right? So how about the next time slot, the next 30 minutes? So A is in the folding step. So so we are folding our clothes, and then the task B is in the dryer, right? So new task C can be assigned to the washing machine, right? So and then the next 30-minute time slot. So A is in the closet step, and then B is in it's a folding step, and then C is in a dryer, then D is in the washing machine. So what's the benefit? So if we just see this time slot, then we can observe that every hardware resource is utilized. So it's every hardware resource is working. Okay. And then also the benefit, what is the benefit? So for every 30 minutes, we can assign new task because if the pipelining is not applied, so and then for this case, the pipelining is not applied, so we can assign new task every 2 hours, right? So every 2 hours. But if the pipelining is applied, we can assign new task at every 30 minutes, right? So what is the speed up? So actually, for this, if the pipelining is not applied, then that it will take the 8 hours, okay? 8 hours. But if the pipelining is applied, then it takes so until the D is complete, then it takes 1.5 and then 2 and 3.5 hours. Okay, so we can reduce. So we can reduce the execution time for multiple tasks. So you need to remember that we can reduce the execution time for multiple tasks. So let's think about let's focus on the single task. Actually, we cannot reduce the latency of the single task, right? So let's compare the execution time of task A only. So for the task A only, so the task A starts at 6 p.m. and then task A completes at 8 p.m. So if we only focus on the execution time, so it's a latency, execution time of a single task, then execution time is the same, right? With the pipelining, right? Because so A starts at 6 p.m. and then task A is complete at 8 p.m., right? It takes 2 hours. But if we have multiple tasks, right? Like A, B, C, D, and then with the pipelining, we can observe that the total execution time of multiple tasks can be reduced. That is the benefit of pipelining. Do you understand? So if we just focus on single task, then the latency is the same, but with the pipelining, we can assign new task every 30 minutes in this example. So which means that if there are multiple tasks, then we can reduce the total execution time. So we can apply this pipelining idea to the processor, right? Because think about the processor. So if the high-level language code is compiled, then we can observe that many instructions, many RISC-V instructions are generated, right? So one application is compiled, so this application includes many instructions. So it means that it is like a single application includes multiple tasks or multiple instructions. So, and then we also learned that when an instruction is executed, then we require several steps, right? So like this one, for the laundry process, then this laundry process includes 4 different steps, and it's the same for the processor. So when a processor executes an instruction, then this processor needs to perform several steps, right? And then if we just apply pipelining idea, and then if there are multiple tasks like this, then we can decrease total execution time. And then the same, a processor needs to execute multiple instructions, okay, like multiple tasks. And then for executing one instruction, then processor needs to perform multiple steps, right? And then if we apply pipelining to a processor, then we can also reduce the total execution time of multiple instructions. That is the benefit of pipelining. Do you understand? I hope everyone can understand. Okay, then how can we divide the pipelining stages of RISC-V processor? So when we design a single cycle processor architecture of a RISC-V processor, we define actually the 5 steps for executing an instruction. The first step is instruction fetch. So the first step is the instruction fetch. So I frequently use IF, it's an abbreviation form. Okay, so which means that an instruction is read from the instruction memory. So this is the instruction fetch. And then the second step is instruction decoding, is ID. Okay, in the abbreviation form, it's ID. So in the ID stage, so in the ID step, the instruction is decoded. So decoding means that a processor so analyze the machine instruction or machine code. Okay, and when the instruction is decoded, then we can access register file. We can access the register file to get read operands. Okay, the required operands from the register file. Okay, so instruction decoding includes the instruction decode and then register read. And then third step is execution. So it is called EX. And then so operands are ready. So the required operands such as the register operands and the immediate operands are ready. And then we can execute required operation, right? So this step is called execution, and then we use the ALU, okay? The fourth step is memory state, okay? So sometimes I use the ME or MEM. So usually I use ME. It's a memory stage. So for the load word or for load or store instructions, so we need to access data memory, right? And then also data memory has delay. So this is the memory stage. And then the fifth step is write back. So I use WB for this step. So the data from ALU or memory needs to be stored in the register file. Okay, so we can just divide the required steps for executing an instruction into 5 steps. So 5 steps. So and then the names of these 5 steps are instruction fetch, so IF, okay, so IF instruction fetch, and the instruction decoding, and then execution, and memory is ME, and then write back, okay. And then so we assume that in order to execute an instruction, then we require these 5 steps. So which means the steps, a single cycle processor can be the required steps of a single cycle processor can be split into or divided into these 5 steps. Okay, so that means in the pipelining, so in this analogy, for a laundry process, okay, for a laundry process, then this laundry process is composed of 4 steps, right? And then so which means the pipelining stage, so each step can be divided into the pipelining stage. So these 4 steps of laundry process is divided into the 4 stages of pipelining stages. Okay, so in the RISC-V processor, we define the 5 steps for executing an instruction. So when pipelining is applied to the RISC-V processor, then we can divide the pipelining stages into these 5 steps, 5 stages, like instruction fetch, instruction decoding, execution, memory, and write back. Okay, so this is very important. So please please memorize that is required 5 steps for executing an instruction. Okay, then so how can we let's think about some benefit of pipelining architecture when we apply the pipelining idea to the RISC-V processor. So this is just assumption. So let us assume that the delay of register read or write is 100 picosecond. Okay, so it's the delay of register read and register write, and then let us assume that each stage, the other stages take 200 picoseconds. So which means that instruction fetch, and then execution like ALU, and then memory. Okay, so these stages take 200 picosecond for each stage, and then the register rate like the ID or write back stage. Let us assume that the ID and write back stages take 100 picosecond for each stage. Okay, Then it should be load word, and then it should be store word. Okay, and then let's compare the required the delay of instructions. Okay, so let's see the load word. So for the load word, the instruction need to be fetched. So it will take 200 picosecond for the instruction fetch, and then register read is ID, so it will take 100 picosecond, right? So for the load word, so x1 and immediate, and the x2 like rs1, this is the RD. So actually the data needs to be read from the register file, right? And then for the load word, then we need to compute the address like x1 plus immediate, okay, rs1 plus immediate. So we need to use the ALU, the execution. So 200 picosecond is taken, okay, and then memory is accessed in order to read the data from the data memory. So it will take 200 picosecond. This is the memory stage, and then for the register write, it will take 100 picosecond. So totally, the load word will take 800 picosecond. This is the delay of load word. And then, as I mentioned in the previous class, the critical path of the single cycle processor is the execution time of load word, right? And how about the store word? Okay, instruction fetch is required. So every instruction needs to be fetched from the instruction memory, and then also store words needs to read register file is 100 picosecond, it's ID, and then the address needs to be computed. So execution it takes 200 picosecond, right? And then for store instructions also needs to access data memory, right? Because we need to store data. We need to update the data memory using store word instruction, right? So it takes another 200 picosecond. But store instruction does not store, does not update. The store instruction does not update register file, right? So the total execution time, total latency of or total delay of the store word instruction is 700 picosecond. And then R format 600 picosecond because the data memory is not accessed by R format, right? R type format. And then BQ does not access the data memory. Also BQ does not write data to the register file, right? So this is the delay of the BQ. But I mentioned that the clock period is determined by delay of the critical path, right? So that is the longest the delay of the longest delay of this execution path. Okay, so what is the longest delay? The longest delay is the execution time of load word instruction, right? So in this case, the minimum possible, the minimum allowable clock period is 800 picosecond. Okay, so this becomes the clock period of the single cycle processor, right? Then how about so single cycle processor? So TC is the 800 picosecond, right? Okay. Then let us assume that we can apply the pipelining. to this RISC-V processor. So the pipelining. So when the pipelining is applied, we just divide the stages of the execution path, right? So we can divide the execution path of this RISC-V processor into 5 stages, as we defined in the previous slide. So we can define 5 stages of the pipeline architecture, okay, pipeline processor, right? So this is the instruction fetch, and then instruction decoding, and then execution, memory, and write back. So there are 5 stages, okay? Then what is the clock period for this pipeline architecture? So for the single cycle processor, this critical delay, the longest delay determines the clock period, right? So it looks like this. This is the flip-flop, and then this is a combination logic, and then the delay, the maximum delay of this combination logic is 800 picosecond, and then this maximum delay decides the clock period. Then how about the pipeline architecture? So what is the critical delay? So what is the longest, the maximum delay of this pipeline architecture? So so in a single cycle processor, we assume that one instruction can be assigned to processor every clock, right? How about the pipeline architecture? If we just think about this pipelining idea, so every task, so like every instruction can be assigned to the duration of each step, right? So what is the longest delay of the pipelining stage? The longest delay is 200 picosecond, right? So which means, at every cycle, then new instruction can be assigned to the pipeline. So firstly, new instruction can be assigned to the instruction fetch stage, instruction fetch step, and then in the next clock, then this instruction in the instruction fetch stage is delivered to the ID stage, and then new instruction can be assigned. So which means the delay of the longest stage, okay, the delay of the state, how can I say? So the stage that exhibit the longest delay decides the clock period. Okay, so what is the longest delay of this pipelining stage? It's 200 picosecond. So which means that we can assign new instruction to this pipeline architecture or pipeline processor at every 200 picosecond. Okay, so it looks like this. So firstly, the instruction A. So instruction A takes 200 picosecond in instruction fetch stage, right? And then the next 200 picosecond, then A is moved to the register read, and then B B is in the instruction fetch stage. So new instruction can be assigned. So A will be complete early. So it will take only 100 picosecond, but B needs to stay in instruction fetch stage for 200 picosecond, right? Because it will take longer. Okay, so A needs to stay in this register read. So that means the instruction decoding stage for the same time. Okay, so the longest delay, the 200 picosecond becomes the clock period of the pipelined architecture. Do you understand? And then, so actually the same clock signal is delivered to the multiple stages. So we need to use the same clock signal, right? So which means that the clock period, so the clock period for each these stages needs to be the same. Okay, so actually in this case we need to use 200 picosecond of clock period. Okay, so because the maximum delay of the pipelining stage is 200 picosecond. Okay. Okay, so let's see the timing of the pipeline single cycle processor and the pipeline processor. So actually this is the load word, is load word, and load word. This is also same load word, load word, load word. Okay, so as I mentioned, each instruction will takes 800 picosecond for the single cycle processor, right? So which means that in order to execute these 3 instructions, it will take 8 picosecond multiplied 3, then 2400 picosecond of execution time. How about the pipelining? So 200 picosecond is the maximum delay. It's the maximum delay of the this pipeline stage. So we need to set the 200 picosecond for the clock period of the clock signal, right? So for the first 200 picosecond, this first load word is in the instruction fetch stage, right? And then for the next 200 picosecond of a period, so it is in the load word, the first load word is in the ID stage, right? It's transferred to the ID stage, and then the second load word is in the instruction fetch stage, right? Right. So with the pipeline architecture, this processor can receive instructions every 200 picosecond. So like the former pipelining analogy, right? Do you understand? I hope. Okay. So, but if we just focus on the one instruction, then the latency can be longer actually. But if we just consider the multiple instructions, so for the single cycle processor, this single cycle processor can receive every instructions at every 800 picosecond, right? But with the pipeline architecture, so this processor can receive instructions at every 200 picosecond, right? So this is the benefit of the pipeline architecture. Okay. Okay. Then let's think about the benefit, the speed up by pipelining. Okay. So if all stages are balanced, so what does that mean? So balanced means that the delay of all stages, all pipelining stages are the delays of all pipeline stages are the same. Okay, it's balanced. So for example, so this is the 800 picosecond is the delay, the maximum delay of, let us assume that 800 picosecond is the maximum delay of the single cycle processor. And then we can divide the steps of a single cycle processor into 5 steps, and then let us assume that the delay of each step is balanced. So which means it's the same. Okay, so which means we can divide the 800 picosecond into the divide 8 picosecond divided by 5. So if this is the 5 steps, so which means that the delay of each pipeline step becomes 160 picosecond. If the delay is well balanced for each stage. Okay, so in this case we can increase the performance by 5 times, right? Because the single cycle processor can receive instructions at every 800 picosecond, but using the well-balanced pipelining architecture, then clock period becomes the 160. Okay, so clock cycle, so clock period of single cycle processor is the 800 picosecond, right? But the TC of pipelined processor becomes the 160 picosecond. When the all steps of pipeline architectures are balanced, so well balanced, then we can compare the performance, like the performance of, okay, perf of pipelining divided by perf of single is, what's this? It's execution time of single cycle processor, and then execution time of pipeline processor. What is this? It's 800 picosecond, because if execution time is proportional to TC, right? And then this is 160 picosecond, so TC becomes the 5. Okay, by definition, we learn the definition of performance in the chapter 1, right? It is 5. Okay, but in the previous example, so what is the clock cycle of the pipeline architecture? Actually the clock cycle, the clock period of the single cycle processor was 800 picosecond, right? But in the previous example, like here, the clock period of the pipeline architecture is 200 picosecond. Why? So as you can see, these steps, right, the delay of 5 stages, the delay of these pipeline stages are not balanced, are not the same. So it's a 200 picosecond, and this is the 100 picosecond. But this 200 picosecond decides the clock period. Okay, there is a longer delay. It's the longest delay. So actually, TC of pipeline becomes the 200 picosecond in the previous example. So it is 200 picosecond. So in this case, the performance is improved by 4. Do you understand? So if we can balance the delay of each stage, then which means that if the delay of each stage is the same, then we can maximize the performance benefit by pipelining. But if the delay of each stage is not balanced, then the performance benefit is reduced. Okay. If not balanced, speed up is less. That's okay. So using the equation we learned in the chapter 1, then we can calculate the benefit by the performance benefit, the performance improvement by pipeline architecture. Okay. Okay, so this slide explains why the RISC-V ISA is good for the pipeline architecture. But it is because the RISC-V ISA is the RISC type instruction, so which means that the instruction decoding and encoding rule is much simpler than the CISC type instructions such as x86. Okay, so and then also the size of each instruction is the same. Okay, so but as you can see, the size of x86 is a various, because it can be 1 byte to the 17 byte. Okay, so this slide just explains that why the RISC-V ISA. So it's a simpler instruction. So like the RISC type instructions are good for designing simpler hardware. Okay. Okay. So until here, so I explained about some basic idea of pipelining, and then we explain about the hazard. So this is also very important concept you need to understand in the pipeline architecture. The hazard. Then what are hazard? What are hazard? What is the meaning of a hazard? What is the hazard? The original meaning of hazard is like this. So this is the very plain surface, and then you can find some crack in the ground. Okay, here. So which means that you can go smoothly on this as normal ground, but if there is a hazard like this, it's like a crack, then you can fall down to this hazard. So which means that you can be slowed down, okay, because of this crack. Okay, so actually this is the normal meaning. So use normal meaning of a hazard, but in a computer processor, the hazard has some different meaning. Okay, so what is the definition of hazard? So this is the definition of hazard. Okay, what is the definition? Okay. The definition is hazards are situations that prevent what? Prevent starting the next instruction in the next clock. So what does that mean? So when we define the pipeline architecture, we assume that the next instruction So when an instruction completes the execution of one stage, and then this instruction is delivered to the next stage, and then new instruction can be assigned to the first stage, right? So which means that at every clock, then new instructions can be assigned. New instructions can be given to the pipeline processor. But because of some reasons or some situations, new instruction cannot be assigned to the pipeline processor. And then this situation is called a hazard. It's called a hazard. So we assume, we expect a new instruction can be assigned to the processor at every cycle. Okay? At every cycle, that we can assign a new instruction to the processor. That's our expectation. But because of some issues, a new instruction cannot be assigned. Then what's the problem? Problem is clock cycles are wasted. So what is our expectation? The new instruction can be assigned to the next cycle. But because of some situations, new instruction cannot be assigned in the next cycle. So which means that clock cycle is wasted. Okay. So this situation is called a hazard. Okay. So which means clock cycle is wasted, right? So because the clock cycle is wasted, so what is the execution time? Execution time is the instruction count multiplied by clock per instruction multiplied by TC, right? So, but if the clock cycles are wasted, so which means that CPI is increased, right? CPI is the number of cycles divided by number of instructions, right? But the instruction count is the same, but number of cycles is increased because clock cycles are wasted. Do you understand? So CPI is increased. So what is the problem? Execution time is also increased, so performance is degraded. Okay, so if we apply pipelining, then clock cycles can be wasted by hazards. So that's why I'm explaining about the hazards in the pipeline architecture. When we learned about the single cycle process architecture, I did not explain about the hazards, right? Because the clock cycles are not wasted. But in the pipeline architecture, the clock cycles can be wasted by hazard. And then, so we can classify hazard into 3 different types of hazard based on the reasons of clock cycle waste. Okay, so the first class of hazard is the structure hazard. The structure hazard, the the reason of hazard is the required resource is busy. So if the hardware resource is busy, then the new instruction cannot be assigned. That is called the structure hazard. So if the required resource is busy, then the instructions cannot be assigned to the target resource. So this is called structure hazard. And then data hazard. Data hazard means that it's caused by data dependency. Data dependencies. So as you can see, need to wait for previous instruction to complete its data read write. So what does that mean? So something like this. So when you write a code, so we frequently use data like the data producer and then data consumer, like the so A equal P plus C and then D equal A plus 1. So if we see that these two statements, and then in order to execute this next statement, then actually the result of A needs to be stabilized. So which means that A needs to be decided, determined. So before A is updated, before D cannot be executed before A is updated. Right. So we can frequently observe these data dependencies in our applications. Right. So actually in the formal statement, we just define some data, and then these defined data are used in the next statement, right? And then data hazard means that the next instruction cannot be executed or cannot be assigned in the pipeline processor because the required data is not ready. Okay, this is called the data hazard. Okay, and then the third hazard is the control hazard. So control hazard means deciding on control action depends on previous instructions. What does that mean? So control hazard means that, so like PQ, X1, X2, and target. So when you execute a branch instruction, then the PC of the next instruction, can be PC plus 4 or PC plus target, right? So like immediate. But in order to know this next PC, then we need to know the result of a branch instruction. So until we know the result of the branch instruction, we cannot know the next PC exactly. So sometimes when the branch instruction is executed, then the branch is true. Like actually, this is normal case for the most instruction, but for the branch instruction has two different PC updates based on the result. But this result will be decided late. So the clock cycles can be wasted until this target of a branch is decided. So wasted, so need to wait until this result is determined. So wait, it's a clock cycles are wasted. So this type of hazard is called the control hazard. Okay, so which means the clock cycle. So structure hazard means that the clock cycles are wasted because of lack of resources. Okay? Because clock cycles are wasted because of lack of resources. This is called structure hazard. The data hazard. The clock cycles are wasted because of data dependencies. So this is data hazard. So control hazard, clock cycles are wasted because of control instructions, like the PQ branch or jump, also other instructions such as the exceptions, okay, control instructions. So there are three classes of, so three different categories of hazard. Okay, so firstly, we need to understand about the hazard. What are hazards? If a clock cycles are wasted in the pipeline architecture, then this is called hazard. This is called a hazard. And then there are three classes of hazard, like structure hazard, because the clock cycles are wasted because of lack of resources, and the data hazard, because clock cycles are wasted because the required data is not ready. Required data are not ready in the pipeline architecture because of data dependencies. So this is called data or data hazard. And then control hazard. Clock cycles are wasted because of control instructions. Okay. Okay, so I will explain the each hazard in more detail. Okay, what is structure hazard? So what is the structure hazard? What is the structure hazard? The clock cycles are wasted because of lack of resources. Why? So this is the hardware. It's some hardware, and then hardware has a limited resources, such as the port. Okay, and then so for example, it's a memory. It's a memory has the address port, okay, right? And then let us assume that instruction A is occupying this memory. Okay, then instruction B cannot use this memory because this memory has only one port. Okay, do you understand this? So because of the limited resources in the hardware, and then if these resources are occupied by a certain instruction, and then the next instruction cannot use this target hardware. So this is the structure hazard. So conflict for use of a resource. Okay. So actually, but so actually, when we learned about the single cycle processor, then there are two kinds of memories, right? So instruction memory and data memory. So it's IMEM or DMEM. Why? Because so there are two kinds of memory, right? Why? Because it is because we want avoid structure hazard. think like this. So actually in chapter 2, we learned actually instructions are also stored in the memory, right? Do you remember? Instructions are also stored in the memory, right? Like the data. But when you learned about the single cycle processor, instructions are stored in the IMEM, and then data. Data are stored in the DMEM. Why? In order to avoid structure hazard. Why? So if we use only one memory, then it's a one unified memory. Then this memory is occupied by fetching an instruction. Okay. So firstly, this memory is used for instruction fetch. So fetching instruction, right? But memory instructions such as load word also or software store word needs to access this memory, the same memory. If we use only one memory, right? Then what's the problem? Actually, every instruction needs to be fetched from the memory, right? So which means that the this memory is used for instruction fetch for every instruction, right? But if we have only one memory, then the memory is already occupied for instruction fetch. Then load word and the store word cannot access the memory because the memory is occupied. Okay. So in this case, when the load word or store word is executed, then the clock cycles can be wasted if we just use one memory, right? Because the memory is already occupied for instruction fetch. Okay. So that's why we separate the memory into the two different memories, like the instruction memory and data memory. So what is the benefit? So instruction memory is always occupied for instruction fetch. Okay. So, and then load word and the store word can use data memory at the same time, right? So we can avoid structure hazard. So actually in the pipeline architecture, we also assume the instruction, there are two memories, like the instruction memory and data memory. So actually the structure hazard is not observed. Okay. But if we just use only one memory, then we can observe structure hazard. Okay. Okay. So let's think about the data hazard. So I mentioned that the data hazard is caused by data dependencies, right? So like this. So this is the example of the data hazard. So an instruction depends on completion of data accessed by a previous instruction. So in this example, the add instruction stores its result in x19, right? And then the very next instruction, the solve instruction, actually use the result of add instruction. Then what's the problem? So this is the execution of add instruction in the pipeline processor. So the first 200 picosecond, it is in the instruction fetch stage, ID, and the next 200 picosecond, it is in the ID stage, execution, memory, and write back. So, this result, the result of this add instruction is updated to register file in write back stage. What's the problem? Sub instruction actually read X19 in ID stage. So, but if this X19 is not updated, then sub instruction cannot read the register file because this X19 is not updated. So if you see that this instruction, then we expect that, oh, X19 is updated here, and then sub instruction uses this X19 updated by add instruction, right? But in the pipeline architecture, the X19 is updated in the write back stage. So actually in the time, the data is updated in this time. Okay. Then if the sub instruction is here, like instruction fetch and ID, so if execution, then sub instruction reads instruction fetch in this time. Okay. What's the problem? It's not updated yet. This is the future and this. So actually sub instruction cannot read the future data. Okay. Do you understand? So actually until the data is updated in the write back stage, the sub instruction cannot read the data from the register file. So write back is updated here, and then actually the sub instruction can read the register file data in the ID stage, actually the later part of the ID stage. So actually the write back stage of the add instruction and then the ID stage of the sub instruction is located in the same time slot. Okay, in order to read the updated data from the register file. So sub instruction cannot be assigned to the processor for 2 cycles. So 2 cycles are wasted. Right. So this is the data hazard because of data dependency. So this is called the data dependency, right? Because the next instruction use the result of former instructions, right? This is the data dependency. But typical, the problem is that the data is updated in the write back stage. So, and then actually the data is read in the ID stage of the next instruction. The problem is, so we need to match the slot of write back stage slot in the same time slot. We need to match the write back stage of the add instruction and then ID stage of the sub instruction. So sub instruction cannot be assigned or executed for 2 cycles. Those 2 cycles are wasted. That's the problem. It's a data hazard. So then How can you avoid the data hazard? So we can use the data forwarding. So what is the data forwarding? The data. So actually, but even though the data is updated in the write back stage of this add instruction, but we know actually the result is already calculated and then already exists in the processor at this time. Do you understand? Because actually the result of add instruction is calculated by ALU. So at this time, we can get the result, right? But this result is stored in the write back stage, but processor has already has the result. So this is the example. So at this time, the add already complete the execution of this operation, and then the processor has already knows the result of this add instruction. And then how about the sub? A sub needs to read the XOR data from the register file, but actually this sub instruction requires data at this time. Do you understand? Because the sub instruction requires data for ALU, okay? So if the data is ready before the execution by ALU, then it's okay. Okay, so data is ready at this time, and then data is required at this time before the ALU, and then so this is the past, and then this is the future, and then it's okay. Okay, so if we just focus on the write back, so that means the register file. The register file is updated at this time, and then if the sub instruction is here, then the sub instruction needs to read the data at this time. So this is not possible because of this is the future and then this is the past. But in this example, actually add instruction complete. So the result of add instruction is computed at this time, right? At this time, and this result is used at this time. So this we can get the result of add instruction before the result is used by sub instruction. This is the future and then this is the past. Do you understand? So this result can be delivered to the input of ALU for sub instruction because this is okay. Do you understand? It is decided at this time, and then after some time, this result can be delivered. So this is called data forwarding. Okay, so because the processor already has the required data, but even though this data is not stored in the register file, then this data can be delivered to the input of ALU. Okay, so the next instruction can use this forwarded data. So this is the data forwarding. So using the data forwarding, we can avoid data hazard. Okay, so in this example, so in this figure, so you can find that so the data is done at this time, and the data is used at this time. Okay, but if the former instruction is the load instruction, then we cannot avoid data hazard using data forwarding. Why? Because the load instruction, the data is set at this time, right? And then if the next instruction use the data by load instruction, there is the instruction fetch ID, and then this is the execution. So actually data needs to be ready at this time, but data will be set at this time. So the next instruction cannot receive the required data at this time because data is set at this time. So in this case, the next instruction needs to be delayed by 1 clock. Okay, so which means that 1 clock is wasted. So we cannot avoid this situation. So in this example, if the former instruction is the load instruction, like load word, then the 1 clock is wasted. So this is the data hazard. So we can observe data hazard if the former instruction is the load instruction, like load word x1 and add x1. Okay. So, but we can apply some compiler optimization in order to avoid data hazard by load instruction. So this is the example. So in this example, so this is the load word. Okay, so we can observe data hazard here and here. So which means that 1 clock cycle is wasted because the add instruction used the data from this former load instruction, right? So, but in this case, if we apply the compiler optimization technique, then we can just adjust the order of instructions, so we can insert some independent instructions between this load and other instruction pair, load and add instruction pair. So this is the example. So we can move this load instruction between this load and add instruction pair, right? So you can find the independent instruction here. So we can avoid the data hazard in this case, okay? Because so we can execute this instruction, and then the data can be forwarded to the next add instruction. Okay. Also, we can observe the data hazard between this load and add instruction, but by inserting another other instructions, we can increase the distance between the load and this add instruction pair. So we can avoid the data hazard. Okay, so using the compiler optimizations, so we can avoid the data hazard like this. Okay. So I explained some detailed behavior of the data hazard. Then for the control hazard, so I will explain about the control hazard. Here. So I will explain about some detailed behavior of control hazard in the next class. Okay. So thank you for your attention, and I hope every student watch this video before the next class. Okay. Okay. So I'll stop here. Then, sorry. See you in the next class.